All right, psychology students, welcome. We're about to tackle two of the biggest, most important topics in biopsychology, localization and lateralization. We are going to cover everything, and I mean everything, you need to know to build a really powerful, nuanced argument for your exam. So, let's get right into it.
So, here's our roadmap for today. We'll kick things off with a huge historical debate about how the brain is even organized. From there, we'll actually map out the brain's key areas before diving into the absolute classic case studies on language, the ones that literally changed everything. Then, it's on to the incredible split brain research, and we'll finish up with the critical evaluation. You know, those super important AO3 points that are going to push your essays to the top of the pile.
Okay, let's begin with the massive question that started this entire field of study. How is the brain put together? Is it one giant do-it-all supercomputer? Or is it more like a massive factory with different departments, where each one has a very specific job to do?
Way back in the early 19th century, this guy, Franz Gall, came up with the theory called phrenology. He was absolutely convinced that the brain was made up of different organs for every single personality trait you can think of, from how much you love your kids to whether you're good at poetry. He thought that if a trait was really strong, that bit of your brain would get bigger, and you could actually feel it as a bump on your skull. Now, let's be clear, the science was totally, completely wrong. But his main idea, that different functions are localized to specific parts of the brain, well, that was revolutionary. It really set the stage for the next 2 centuries of debate.
So this is the fundamental conflict you have to get your head around. It really puts two completely opposite theories head to head. You've got localization of function on one side and the holistic theory on the other. So on one hand, you have the holistic view. This suggests that the whole brain works together for pretty much any behavior, that things like memory or language are spread out across the entire structure. But on the other side, localization theory says no, specific functions are tied to specific identifiable areas. For a long time, the holistic idea was the one most people believed. But as we're about to see, the evidence from the 19th century onwards started to cause this huge dramatic shift towards localization, all thanks to some incredible discoveries from patients who had suffered brain damage.
Okay, before we can even start talking about where something as complex as language lives, we need a map. So let's go ahead and establish the major territories of the cerebral cortex, that wrinkly outer layer of the brain that houses all our higher mental processes.
So, the cerebral cortex is split into 4 main lobes, and these are mirrored on both the left and right sides. Right up at the front, we've got the frontal lobe. That's your hub for thinking, planning, and movement. Behind that, at the top, is the parietal lobe, which deals with sensory information. All the way at the back, we have the occipital lobe, which is dedicated to vision. And then on the sides, kind of tucked in by your temples, is the temporal lobe, responsible for hearing and language. Now, inside each of these lobes, there are specific cortices with very distinct jobs.
For the exam, it's absolutely vital you can link each cortex to its lobe and its function. So the motor cortex is at the back of the frontal lobe, and the somatosensory cortex is at the front of the parietal lobe. See the pattern here? Both of these areas operate contralaterally, which just means the right hemisphere controls the left side of the body, and the left hemisphere controls the right. This is such a fundamental concept. So let's say a person has a stroke that damages the motor cortex in their left hemisphere. Well, they would experience paralysis on the right side of their body.
Right. Now let's get to the classic evidence that really hammered home the theory of localization. This is the story of how neuroscience found out that a uniquely human skill like language isn't just floating around everywhere in the brain, but is actually tied to very specific spots.
This one word, ton, represents one of the most famous case studies in all of psychology. It belongs to Louis Victor Le Borgne, a patient of the French physician Paul Broca. For years, Le Borgne could understand everything people said to him. He was clearly intelligent, but the only sound he could actually make was the syllable ton. Just imagine the frustration. This pointed to a very specific problem, not with understanding language, but with producing it.
And here it is, the breakthrough moment. After Tan passed away, Broca performed an autopsy, and what did he find? A lesion, a clear area of damage in a specific part of the left frontal lobe. He then studied 8 other patients who had similar problems with speech production and found they all had damage in the exact same spot. This was it, the first solid anatomical proof linking a complex cognitive function to a specific bit of brain, which is now and forever known as Broca's area.
Now, get this. Just a decade later, a German neurologist named Karl Wernicke identified patients with the exact opposite problem.
They could speak perfectly fluently, but their sentences were complete gibberish, often filled with made-up words or neologisms. And crucially, they couldn't understand what other people were saying to them. Wernicke traced this problem to damage in the left temporal lobe, in what we now call Wernicke's area. For your exam, being able to clearly tell the difference between Broca's expressive aphasia and Wernicke's receptive aphasia is non-negotiable. Just think, Broca's is broken speech, Wernicke's is word salad.
And this shows us it's not just about isolated spots, it's about a connected network. When we hear someone talk, the sound information goes to Wernicke's area to be understood. If we want to reply, the meaning gets worked out there, and then it's sent along a neural pathway over to Broca's area, which then creates the motor plan to actually say the words. This is a brilliant, sophisticated point for an essay. It shows that even though functions are localized, they work together in a circuit. It's both localization and connectivity.
Okay, so up to now, we've been focusing on localization within a hemisphere, mostly the left one. Now, we're zooming out to look at lateralization, the idea that the two hemispheres themselves aren't identical twins. Nope, they're specialized for completely different jobs.
Roger Sperry's Nobel Prize-winning research from the 1960s just completely flipped our understanding of the two hemispheres on its head. He studied a really unique group of patients who had undergone something called a commissurotomy. This is a really drastic surgery where the corpus callosum, that massive bridge of nerve fibers connecting the two halves of the brain, is cut. It was a last-ditch treatment for severe, uncontrollable epilepsy, but it created this amazing natural experiment, a chance to study each hemisphere completely on its own. Sperry's method here was just genius. See, in a typical brain, information that comes into one hemisphere is instantly shared with the other across that corpus callosum bridge. But in his split brain patients, that bridge was gone. This meant he could isolate them. By flashing an image really fast to a person's right visual field, he could send information only to their left hemisphere. And by flashing it to the left visual field, he could send it only to the right. He could basically now talk to each half of the brain separately.
And this is the killer finding. When a word like face was flashed to the right visual field, that information went straight to the language-rich left hemisphere, and the patient would just say, "Yep, I saw the word face, easy." But when the word was flashed to the left visual field, the information went to the mute right hemisphere, and the patient would say they saw nothing at all. Yet, and this is the incredible part, when they were asked to draw what they saw with their left hand, which is controlled by that very same right hemisphere, they would draw a face. The right brain knew the answer, it just had no way to say it out loud.
Sperry's work completely changed the game. It showed that the hemispheres weren't one dominant and one minor sidekick, but were actually two specialized partners. The left hemisphere is like the analyst, the talker, dealing with logic and language. The right hemisphere is the synthesist, the artist, great at spatial awareness and recognizing faces. They work together so perfectly that we have this single, unified sense of reality.
All right, now for the part that separates the good answers from the truly great ones, the AO3 evaluation. You have to be able to critically analyze these theories and studies, so let's unpack all the strengths, weaknesses, and counter-arguments.
As amazing as Sperry's research was, it's not perfect. First off, the sample size was tiny. We're talking about 11 patients taking part in the main studies. That makes it really hard to generalize these findings to everybody else. But more importantly, these people were not a neurotypical control group. They all had a history of severe epilepsy. It's totally possible that years of seizures had already caused unique changes in their brain function. This is a massive confounding variable. We just can't be sure if the differences he saw were because of the surgery or because of their pre-existing epilepsy. This is a really powerful criticism to bring up in your essays.
Okay, now let's bring in a direct challenge to the whole idea of localization. While Broca was pointing to specific spots, Carl Lashley's work with rats suggested the complete opposite. He taught rats to run a maze, and then he removed different parts of their cortex. He found that their memory for the maze wasn't affected by which part he removed, but by how much he removed. This led him to two big ideas: the law of mass action, which says performance depends on the whole cortex working together, and equipotentiality, the idea that other brain circuits can take over the job of damaged ones. For a complex task like learning, it really seems like the brain works more holistically.
This table is a fantastic revision tool for structuring your arguments. You've got the powerful case studies of Broca and Wernicke on one side, plus Sperry's controlled experiments, all pointing towards strict localization. But on the other side, you've got strong counter-evidence from animal studies like Lashley's and also the modern concept of brain plasticity.
You know, the brain's incredible ability to reorganize itself after damage, which gives a lot of support to a more holistic, flexible view.
And this brings us to a more modern, blended view. Maybe the debate isn't really about localization versus holism, but about how they work together. This quote suggests that the hemispheres themselves might actually represent these different styles. The left hemisphere is analytical. It breaks things down into small parts, which is perfect for language. The right is holistic. It sees the whole pattern, the gestalt, which is perfect for recognizing a face. So maybe the brain is both localized and holistic. It just depends on the task at hand.
So, as you prepare for your exam, the most sophisticated answer isn't about picking a side. The modern view is that no function really happens in total isolation. Instead, the brain seems to operate as a massive network of specialized hubs that are all densely interconnected. The question isn't so much if functions are localized anymore, but how these localized hubs all communicate and work together to create our seamless, complex experience of the world. Good luck with your revision.